Now that we've talked about the method of separation of variables, and we've seen a few specific examples, let's look at a really applicable problem, a really real-life application where we will use separation of variables to solve a differential equation. We're going to talk about Newton's law of heating and cooling. We've seen this before. We've actually set up the differential equation for this problem in a previous video, but let's work through it again because it's important to really understand this application and how we can model this physical scenario with a differential equation. So Newton's law of heating and cooling says that the rate, we want to think here when we see rate about derivative, the rate at which the temperature of an object changes over time is directly proportional to the difference between the temperature of the object, H, and the constant temperature of its surroundings, T. So we want to set up a differential equation to describe this physical phenomenon. So first let's focus on some key words here. We have the word rate, and this is the rate at which the temperature of the object changes over time. So rate, that's the rate of change of h, and we want to think of the rate here as a derivative. So the rate of change of h with respect to time, this is dh dt. That's the rate at which the temperature of the object changes. We could also call it h prime of t if we wanted to, but I think it's a little bit more useful here to think of dh dt. So dh dt is the rate at which the temperature of the object changes over time. We're told that it is directly proportional to the difference between the temperature of the object, which is just h, and the constant temperature of its surroundings, T. So let's highlight this word difference. The difference here between the temperature of the object and the temperature of the surroundings, this is temperature of the object minus the temperature of the surroundings. And Newton's law says that this rate is directly proportional to this difference. That means that the rate, dh dt, is some constant times the difference h minus t. So here we have the differential equation that describes Newton's law of heating and cooling. K and T are both constants here. These are both just some values. H is how we usually think of y, and our independent variable here is t rather than x. So really we have a differential equation here, and it's autonomous. Notice this. This side of the equation does not have any of the independent variable. There's no t's. So this is an autonomous differential equation, and we'll be able to solve it using separation of variables. So now that we've set up the differential equation, let's work through solving it. So we're working on example 6a here. We just found that the differential equation is dh dt equals some constant k times h minus t. T is the constant temperature of the surroundings. K is some constant that depends on the type of object that we're looking at here. So K and capital T are just constants. They're going to make things a little bit messy, but we just want to keep in mind that these are constants like 2 or pi or whatever. They're just numbers. Now we want to solve this using separation of variables. I'm going to take the h minus t and I'm going to move that to the other side. H here is how we normally think of y. So I'm going to move h minus t to the other side and then multiply both sides by dt. So to separate variables, I have 1 over h minus t dh equals k dt. I only have t's over here. I only have h's over here. Once again, capital T is just a constant. K is just a constant. So now we can integrate. And when we integrate this expression here, we're focusing on h as a variable. So this is going to be a natural log. So it's natural log absolute value of h minus t equals the antiderivative of k, which is constant. The antiderivative of a constant is the constant times the variable. And then we're going to add here plus an arbitrary constant c. We want to solve for h. This is the heat function that we're looking for. This is the temperature of the object. And if we solve the differential equation, we will have a function that gives us the temperature of the object at any time t. This step right here is very similar to a couple of examples that we've already seen. In particular, example 1b, we worked through solving the differential equation y prime equals y. And we ran into a step that looked just like this, and we worked through talking about the value of this constant and how it changes to just an arbitrary positive constant and then changes back to positive or negative. We worked through all that. So in this step, I'm just going to gloss over those steps. Imagine taking e to the power of both sides, and then continue from there to solve for h. And we would get here h minus t equals an arbitrary constant times e to the kt. Again, I'm skipping some steps here, but look at the example 1b, and we'll see pretty much the same exact steps that we would use here. So I'd encourage you to fill in these missing steps to make sure that you're comfortable with that process, but this is what we'll get solving for capital H. So now I can solve for capital H all on one side of the equation. So H equals C e to the kt plus capital T. So this is the general solution to the differential equation for Newton's law of heating and cooling. And when we're working through an actual physical sort of example, when this has a tie-in to a real-world problem, lots of times the arbitrary constant has an actual physical meaning, and that's the case here. So we can actually find an expression for this arbitrary constant C that really means something physically. In this case, let's look at the temperature at time 0, and let's just call this H of 0. This is the initial temperature of the object, H sub 0. So we'll say this is the initial temperature of the object. That's the temperature of the object at the start of the experiment at time 0. And we can plug in 0 for T to find an expression for C here. So we have C times e to the k times 0 plus T. E to the k times 0, that's just e to the 0, which is 1. So I have C times 1 plus T. Remember, T is just some arbitrary, well, it's a meaningful constant. It's the temperature of the room, but this is just some constant. H sub 0 is the initial temperature of the object. So I have C plus T equals H sub 0. So I can solve for C. C equals the temperature of the object at the start minus the temperature of the surroundings. That is the physical interpretation for this constant C. So I can write this H function using that value for C. The temperature of the object, and now I'll write the temperature as a function of time. The temperature of the object at any time t is C. Now we replace C with H sub 0 minus T. So it's H sub 0 minus T times e to the kt plus the initial the temperature of the surroundings. Here is the solution to Newton's law of heating and cooling, and we could find that using separation of variables. Depending on which situation we're talking about, depending on what the initial temperature of the object is and what the room temperature is, we'll get different functions here which will describe the temperature of the object at any time t. So we'll use this equation in the next couple examples. So with this equation in mind, let's look at example 6b. I want to set up a function that describes this scenario. And this I actually made a cup of coffee yesterday, and I measured the different temperatures here so that I could have a real-world applicable sort of situation, and I'll show you a graph of what this looked like in a little while. So I brewed a cup of coffee, and I do brew coffee a lot warmer than 169 degrees, but the brewing process takes a while, and over the brewing process the coffee cools down. So even though I started with near boiling water, by the time I had finished brewing, the coffee had cooled down to 169 degrees. So I measured the temperature right after I was done brewing. That's the initial temperature. We'll call this H sub 0. And after 10 minutes, I measured the temperature of the coffee and found that it cooled to 145.9 degrees. The room temperature was 75 degrees Fahrenheit. It was a little bit warm. But nonetheless, we can use all these values to find actual values in the function that we just solved for Newton's law of heating and cooling. And we'll find a function that describes the temperature of the coffee at any time t. Here we go. So in example 6b, so first I'm just going to write down that function that we solved using separation of variables. The temperature of the object, in this case coffee, is the initial temperature minus the surrounding room temperature times e to the kt plus the surrounding temperature. So in this case, we're told that the surrounding temperature was 75 and the initial temperature of the coffee was 169 degrees. So we can use those different values in this expression here. So we have h of t equals 169 minus 75. That's just 94. E to the kt plus the surrounding temperature, 75. Here's the problem. I still have this k. I want the temperature of the coffee cup at any time t, but I've got this constant k. I can solve for this by using the extra piece of information that we were given. When I measured the temperature of the coffee after 10 minutes, I found that it had cooled to 145.9 degrees Fahrenheit. That means that the temperature at time 10 minutes was 145.9. Now, this is what I'd get if I plugged in 10 for t. So I'm going to plug in 10 for t here, and then I'll have an expression where the only unknown is k. I can solve that, and find the value for K. So h of 10 equals this 145.9 degrees, and now I'll put in 10 for T. This also equals 94 e to the K times 10 plus 75. Now I want to solve for K. So to solve for K, I'm going to subtract 75 from both sides. I'll have 145.9 minus 75. This equals 94 e to the K times 10. I'll divide both sides by 94. If I divide both sides by 94, it cancels on this side. So I have e to the K times 10 equals this fraction here. And then to solve for K, I want to take the natural log of both sides. So I'm going to take the natural log of both sides, and this stuff cancels. So I've got the natural log of e to the K times 10, and the natural log and the e, those cancel. So I have K times 10 left over here. And now I'm going to divide both sides by 10 to get the value of K. So these 10s cancel, and I get the value for K. So this was a little bit unconventional how I solved it here. Solving for K is not really the point. For all I care, we could put this into Mathematica and solve for K. But here's the value for K, and this is approximately equal to negative 0.0282024. We'll just use negative 0.0282. So this is the value for K. Now that I've got the value for K, I'm going to take this value for K and plug it up here into the equation that describes the temperature of the object. So here's my grand final answer for the equation that describes the temperature of the coffee at any point in time. 94 e to the negative 0.0282 T plus 75. So for my specific example with my cup of coffee, I could find the temperature of the coffee at any point in time simply by plugging in T values, and that would give me the temperature of the coffee. So here's the answer for part B. Before we talk about the rest of the parts for problem 6, let's go ahead and look at this function in Desmos. So here we are in Desmos. The y-axis here is measuring temperature in degrees Fahrenheit. The x-axis is measuring time in minutes. And here, this is the initial point at time 0 where the temperature of the coffee was 169 degrees. And at 10 minutes, the temperature was 145.9 degrees. And these are real temperature readings. I had a real cup of coffee where I actually found these temperatures. So this is actually describing a real life scenario. Here is the equation that we just found. It's 94 times e to the kt. We just solve for k here. And notice that it passes through these 2 points. So this graph is describing the temperature of the coffee at any time t. So we can see after 5 minutes, the temperature was around, something like 156.5, somewhere like that. And if we zoom out here, this is actually an exponential function. The coffee temperature decreases exponentially. Now, when I measured the temperature of the coffee yesterday, I actually measured the temperature at 1-minute intervals from time 0 to time 10 minutes. And I got these data points right here. Now, looking at these data points, it doesn't really look like exponential decay. It almost looks linear. So if we could fit it with a line, that's what it would look like. And that almost looks maybe like it'd be a decent fit. We have some fluctuation here, and that's probably because I wasn't in a super controlled environment and my thermometer wasn't super accurate. But I actually measured some temperatures beyond 10 minutes. And those temperatures look like this. And they're starting to stray a little bit further from this linear fit. So all of a sudden, linear doesn't look so good. But if we look at the exponential function that's given to us by Newton's law of heating and cooling, watch how much better of a fit that is to these points. It really fits them much closer. So exponential cooling of the coffee is what's going on here. And even though there's some fluctuation in these actual physical readings, we can see that they line up pretty closely with the equation that Newton's law of heating and cooling gives us. Let's work through the rest of example 6. Now that we found a temperature Let's work through the rest of example 6. Now that we've found a function which describes the temperature of the coffee at any time t, we can answer question C very easily. What was the temperature of the coffee an hour after brewing? Also, letter D will be pretty easy as well. We want to know how long did it take for the coffee to reach a drinking temperature of 120 degrees Fahrenheit. Let's take a look at these. So for example 1C, we want to know what is the temperature of the coffee after an hour? So let's write down the temperature function that we found. The temperature of the coffee at any time t is 94 e to the negative 0.0282 t plus 75. There's the function that we found. So for part C, what's the temperature of the coffee after an hour? Well, this is simply h of 60. So we just plug in 60 for t, 94 e to the negative 0.0282 times 60 plus 75. Plug this into Mathematica and we get 92.3 approximately. So 92.3 degrees Fahrenheit, that's the temperature after 1 hour or after 60 minutes from when the coffee has been brewed. Now, question 6D, oh, this should be a 6. Question 6D is trying to answer the question, when is the temperature of the coffee 120 degrees Fahrenheit? So we want to know at what time t is h of t equal to 120. So we're going to set h of t equal to 120 and solve for t. So set 94 e to the negative 0.0282 t plus 75, set that equal to 120, and solve for t. Now, we could work through the steps by hand if we wanted to, but I just plugged this into Mathematica, and I found a t value of t equals approximately 26.12. So this is saying at about 26 minutes, the coffee is the temperature that I'm looking for, 120 degrees Fahrenheit. So I hope you have an appreciation for how useful this function is. We could only find this using differential equations, and this function will tell us the temperature of the coffee at any point in time. If we want a certain temperature, we can find exactly what time gives us that temperature. This is a very useful model for this real-life physical situation. Let's go ahead and modify this problem slightly, and let's answer part E. Suppose that I'm impatient, and I place my freshly brewed coffee in the freezer, which has a temperature of 0 degrees, so this will be the new T, because I want to cool it faster. Now remember, Newton's law of heating and cooling says that the bigger the difference is between the temperature of the object and the temperature of the surroundings, the larger the value of the rate of change. So this makes sense. The larger the difference between the temperature of my coffee and the temperature of the surroundings, the faster it'll cool down. Coffee will cool down faster if you put it in the freezer. So I put it in the freezer to cool down. After 10 minutes now I measure the temperature, and before, after 10 minutes at room temperature, it was 145.9. Now, much colder, 130 degrees. So it's still not quite at my 120 degrees that I'm looking for. So since it still hasn't reached my desired temperature, I put it back in the freezer. And then if I forget about it, because I'm having so much fun solving calculus problems, I want to know how long will it be until my coffee freezes, which is 32 degrees Fahrenheit. Now, I don't tend to forget about coffee, so this isn't really very realistic, but let's go ahead and solve it anyway. So to solve this one, we need to go back to the original equation that we had from solving Newton's law of heating and cooling. So for 6e, the original equation that we solved using separation of variables was h sub 0 minus t times e to the kt plus t. And here, in this case, the temperature of the surroundings, this is the temperature of the freezer, and that is 0 degrees. So capital T equals 0. The initial temperature of the coffee is still the same, 169. So h of t, using these values, is 169 minus 0, so 169 e to the kt plus 0. So here's the equation that's describing the temperature of the coffee when it's in the freezer. Now, we still need to solve for this value of k. We can solve for that value of k by using the extra little piece of information. We were told that at time equals 10, the temperature of the coffee is 130 degrees. So this tells us that h of 10 equals 130. So we're plugging in 10 for t. So this equals 169 times e to the k times 10. Now, we worked through all the steps when we solved this equation last time for k. So we'll skip those steps here and we'll just plug this into Mathematica and find the value for k that way. So after plugging into Mathematica, I found that k is approximately negative 0.0262. Now we can write the entire function that models the temperature of the coffee. h of t equals 169 e to the negative 0.0262 t. We want to know, when does the coffee freeze? In other words, we want to know at what time is the temperature equal to 32. So I'm going to solve h of t equals 32. So this would be 169 e to the negative 0.0262 t. And once again, I'll rely on Mathematica to solve this. And plugging that into Mathematica, I get t equals approximately 63.52. So about 64 minutes after I've placed the coffee in the freezer, the coffee freezes. Once again, this is an incredibly powerful description of this physical phenomenon. We can describe the temperature of the coffee using Newton's law of heating and cooling. Now very briefly, let's compare this function, which models the temperature of the coffee in the freezer, with the one that we found earlier, measuring the temperature of the coffee when it's just sitting out in the open. So once again, on the y-axis we have temperature, on the x-axis we have time measured in minutes, and here was the original description. This is the curve describing the temperature of the coffee over time when the coffee cup was just left out in the open. If we take the coffee at the same initial temperature and put it in the freezer, here's the function that describes the temperature over time. We see a much more drastic cooling here, and after 10 minutes in the freezer, the coffee is much cooler, 130 degrees now, and we can see when the coffee reaches freezing in the freezer, that's 32 degrees Fahrenheit. That's right about, well, let's see, 32 degrees is right here, and that's that 63.5 value that we just solved for. So the coffee will freeze at that time. So using Newton's law of heating and cooling, we have some pretty accurate descriptions of the temperature of the coffee.